Well, good morning, everyone. My name is Marianne Steidinger, and I'm here with Greg Olsen, who's Senior VP of Products from Falkonry. Today, we're going to talk about pattern recognition for time series data in OSIsoft PI. This was a lab that we conducted at the OSI user conference last month. So with that, I'm going to turn it over to Greg.
Okay. Hi, everyone. As Marianne mentioned, this webinar is really to describe the Falkonry product and how it can make it easy to add pattern recognition to time series data-related applications. And we're specifically focused on the OSIsoft PI data system for this webinar. Just quickly about the company. Relatively small company, but we've been around for 4 years. We have a headquarters in Sunnyvale, California, and we have an office in India as well. We were venture capital funded. Our team is really made up of a mixture of various engineering disciplines and computer science. We have PhDs in many different engineering disciplines as well as in computer science. So our skill is really at packaging machine learning in a way that makes it usable by subject matter experts in various domains like manufacturing, electronics, etc. So the areas of customer involvement we've had have spanned many different types of industries and different problem types. So many of the examples are in the process industry, but we've also done some work in data centers, as well as telecom. To sort of get a just basic sense of what we do is we take time series data, so operational data that could be sensor data, logs, whatever information, the type of stuff that typically gets put in a historian like PI, and then look for patterns in that data that might reveal interesting condition information about machines, processes, equipment. I think most people know that there's patterns in data, but once you start going multivariate, where you're looking at patterns across 5, 6, up to hundreds of signals, it becomes very difficult to see patterns in a typical engineering model-based approach or through using thresholds or other basic rules. So the Falkonry product is really a pattern recognition engine that automates the identification of these patterns across time. So across a set of different signals, finding bands of particular repeated behavior, and then feeding that back to subject matter experts who impart meaning to those different patterns. So Falkonry works inherently with the subject matter expert whose job it is to provide meaningful labels like a condition of overheated, broken, etc. Just to sort of make this a little bit more concrete, there's lots and lots of different cases where there's some form of signal data and some condition that might be revealed by that data. So if we looked at a fleet of trucks and we're measuring acceleration, turn angles, various inputs to the engine, we may be able to determine things like the state of the vehicle or the state of the driver. Likewise, in agriculture, there's a lot of effort to instrument livestock to find things like health conditions, or if they're in a pregnancy or in the process of having birth. The more likely case in what we see in the PI case is machines that have sensor data that gets logged that could reveal conditions that lead to a maintenance event or potentially some efficiency improvement by recognizing that condition before it occurs. I'll just note one customer that I've spent a fair amount of time with. I think it's an excellent example of how Falkonry can be used. Is a mining company that's located in Wyoming called Jinner that mines soda ash or mines a raw mineral and turns it into soda ash as their final product. They were having a lot of issues with downtime in that the variability in the ore would cause a downstream shutdown of one of the critical components, which in this case was a vertical ball mill. They tried many different ways to look for patterns in the data through engineering models. They'd even had an outside data science team try to build a model, and with really limited success. In a very short period of time, we introduced Falkonry, and they were able to see just from patterns in the basic temperatures and currents upstream from this mill, they were able to recognize up to 12 hours in advance conditions that corresponded to changes in the ore composition that would ultimately have caused a problem downstream. And then they were able to feed that into their control system to regulate the feed rates to avoid a downtime event. So really, where Falkonry is different than many other data science or machine learning approaches, it's really about packaging machine learning inside of the box, specifically for this problem of multivariate pattern recognition, without the requirement for software development or data science. And that in doing so, we have a much more accountable approach as well for the people who are tracking what's going on. So how this works with Pi. So this is a typical Pi system diagram where we see the components of the Pi system, and there's some associated monitoring application that's using data in Pi to let users know what's going on with their system. Falkonry is really introduced as an add-on that has a small piece of software that runs close to the Pi server, we call the Falkonry Pi agent, that's really responsible for sending data to the Falkonry system, which can be running either locally on premise or in a cloud environment. It's really a standalone engine that receives data from Pi, allows users to build a model, and then once the model is ready, it will feed the data back into Pi. So at the end of this process, Pi is enriched with a new stream of condition information that can then be used in the monitoring applications that already exist, can use the Pi notifications or event frames, any of the mechanisms that are available in your application. To see sort of the range of how this might play out, a typical situation is an integration agent talks to the time series data store, and it can communicate historical data that can be used to build a model, and then can also stream the live data for real-time recognition. It's possible also to configure the system where you separate those two activities, where learning could be done centrally on one server, and then you could have smaller servers for recognition with lower latency distributed, close to the machine or the process line or what have you. We've seen cases where this, can map across various sites and geographies. So this is something we can talk about if anyone is interested. Okay. What's going on inside of Falkonry with this stream of signal data? And in Falkonry, just for terminology, we use the term signal. Signal maps directly to tag or attribute in Pi. Our result we call an assessment, and again, that just comes back and it looks like another tag or attribute in Pi. So what's going on in the stream of data is Falkonry is taking the stream of signal data, doing a fair amount of signal normalization. So what that involves would be things like doing frequency content analysis, signal normalization to get it ready for the machine learning, compression, other ways to basically make the data more amenable to the downstream machine learning. The second step is really the kind of core of what's going on, is trying to extract temporal features out of each of these signals. What's underneath is an approach called independent component analysis, which is really looking for sort of characteristic shapes. And this this family of algorithms derives from a lot of biological examples where people are looking at cardiac rhythms and things like that. The basic idea is you're looking for representative characteristics, patterns that might repeat, and then looking at those across each of the individual signals and then pulling it all together to create a feature vector that's representative of what's happening as we go along. And I'll show this in context, and it'll be a little bit easier to grasp. After that, we go into more traditional classification techniques where we cluster the data so we can classify what's going on without having any ground truth or facts. Then once we add facts which come from the subject matter experts, or maybe from inspection systems or downstream quality measurement systems into the system, then we're able to further classify the data using traditional techniques like random forest. Okay, so so just to get oriented, I'm gonna go to a PI system where we have a few databases and some basic examples. So what I'm going to start with is a very simple example that I just generated, where there's some analyses that basically use random numbers to generate a set of signals for these two machines of the same type. So what you're looking at here is the interface to the Falkonry PI agent. So this is the piece of software that's used to configure, what data from the PI system do I want to send to Falkonry, and where do I want to put the result, that Falkonry gives me back. So I'll just go ahead and start a new one. So we'll call it my machines. We'll notice a couple things here. First, I tell the system which Falkonry service I'm going to connect to. So this URL and this token correspond to an account that I have on Falkonry. So again, this instance could be running locally on your site or in your cloud environment. And we also have a publicly managed cloud for purposes of doing pilot and proof of value experiments. That token that you saw there is the way that the agent's able to authenticate itself to Falkonry. So basically, you tell the system, I want to generate a token, and you just cut and paste this token over into the PI agent window. We'll see that it also shows the local PI system that this is connecting to. So this requires ACID framework. So it's connecting to the AF database there. And then I can find that example that I showed. Its template. So basically, we key off templates, and from templates, we pick the set of attributes that we'd want. So these are some signals I created previously, but these 4 signals that you see here are the 4 raw signals that are being generated. Here I can also say I want to do this for all the machines that are associated with that element template. Then I get into this history window. So this is where from PI I want to share some pre-existing set of data in order to build the model from. So in this case, I'm just going to go back like a half hour. So these machines are basically producing signal data every second. When I'm done, I want to put the result back into Pi. So I could tell Pi I want this result. So what it's doing right now is it's interacting back with Asset Framework to create an attribute to hold the result. So now that I've done this, I'm going to save what we call a data stream. So a data stream is the basic building block in Falkonry. So that's what instantiates the connection between a set of data from Pi back to Falkonry. Okay, so we now see that there's a connection to Pi, connection to Falkonry. I haven't turned on live monitoring yet. I'm going to go now back into the Falkonry world, and I'll see that you know, it'll take it a few minutes, but okay. Well, I'll look at my cooking show pre-existing version. Sorry. So what you see here, we'll turn off this, is the data from Pi shown in Falkonry. So at first, when you make a data stream connection, you really only have the signal data. So here we'll see these 4 signals, and we'll see them for the 2 different machines. So each machine is represented. I can look at just one of them at a time or both. In this user interface, I can do things like zoom into the timeline to look more closely. And then the core function I do is create models. So when I create a new model, I'm selecting the time range I want to use, and then I can give it some guidance. So things like bounds on time range, the rate at which I want the result to be sent back into the target system. So here we'll see, in the case, the first model I made, I didn't give it any label information. I just told the system, hey, look at this data, try to find patterns in it. So what these bands represent are periods of distinct patterns that resulted from the feature learning and the clustering on that data. So here I see there's, you know, 4 different colors. They're called unlabeled 1 through 4. The system could find up to 10 because that's the bounds I set on this. Basically, it's just looking for transitions in state. And again, this data isn't really representing, you know, there's random generated behavior. So you're going to see sort of a smattering of things that might not reveal any true patterns as you would in a machine, you know, that had actual behavior, but at least give you a sense of how this how this works. So the next thing that you would do is start adding labels. So here, I just put in a few labels that said, I think this light blue is normal. I'm going to label this one as C1. And the basis for doing this would typically be external observation through inspection systems, quality measurements, whatever information is available that might be used to correlate, what was going on at that particular time. And then these labels then will be incorporated by Falkonry into the model, so that when I build the second model, I'll see now that it generalized from these patterns and filled in a fair portion of the space, but not all of it, with the new labels. So if I go back. So these bars at the top are summary bars. So basically what's going on here, it's showing for both machines. In the unsupervised case, it found this distribution of content of each of those 4 unlabeled. The summary bar will zoom in to that section, and this will tell you what percentage was spent in each of those conditions during that time window. So then we'll see for the second model, we have 50% spent in this normal, and then reduced amounts of time in the other conditions, and then still some of the unlabeled, it wasn't able to map. And again, I'm going to run through an example with some real data, and this will be more apparent. Okay, so okay, so if we look at what's going on here, as I build a series of models, those have different fidelity, have different amounts of label. I can tell the system which model I want to be active, and then I can make this this pipeline be live, or this this data stream, so that now those models will be applied to live data that comes out of the PI system through the agent and then back into PI. So I'll go to the already running version. So for the one that was previously created, the result is going into this variable called condition. So what's happening right now is any new data that streams through the agent goes off to Falkonry, gets the condition label applied, and then comes back into PI. This result is the one that I created with the newly created version, but if we can see here, we'll see that over time, the system is generating a series of these labels, and they're going back into the PI system. So here's the one that I created, just so you get a sense. So here, there's no models yet, none in the views I can see. So the way that this, if I go back to the beginning, we'll see here, I'll add a segment. Here, I want this to be, smaller. And again, any of this adjustment of parameters, ultimately, it doesn't take that long to run these models. So basically, there's some experimentation of which labels, which conditions did I label, how many of those you really can experiment and run these models and then test them against the rest of the data that you have to get to a good model in a relatively short period of time. As I mentioned with the mining company, they really on their own just created a dozen models, found what they wanted in a period of 2 weeks, just cold start with Falkonry. Yeah, so the thing I didn't point out is, for this case, this was a relatively small amount of data. It was taking 3 minutes to create those models that we were able to see then. Okay, so let's look at a slightly more interesting example in Pi. So there's a condition management example in the Acid Framework example kits that are available online from OSIsoft. In here, this case has a variety of different equipment and some simulated data and some built-in condition monitoring. And so this is really a way to look at how Falkonry could be used to complement existing condition management approaches. So thresholds, sort of excursion realms, all those things are very useful, but sometimes just doing purely data-driven pattern recognition, from the raw data can give you something extra. So what I'm going to do here is show how, the core signals are really this inlet pressure, the outlet pressure, and the pressure drop. How could I do this, with Falkonry? So we'll create a new data stream. Having a little bit of network challenges today. So this heat exchanger, I'm just going to selectively pick 3 attributes of interest, and there's only one element associated with this, but I'll do all. In this case, I might, look for a bigger chunk of time. So I know from this example that I want to go back all the way to August. I'm going to give it a better name. Okay. Okay, so I can look at previous example. So yeah, one thing I didn't do there that I feel is, one way of getting facts into Falkonry is to use event frames. So in this particular case, there's an event frame that corresponds to this. I'm going to put this in. Comcast is not my friend today. Okay. Okay. So I'm going to go back to the previously saved heat exchanger. Oh, it's loading. created a couple models here. So in this example, I have behavior. Oh wait, sorry. I'm going to use another one. This one has the Pi supplied event frames. So these signals have a sort of repeating behavior. It's basically a simulation from the AF example kit. When I ran the first model, unsupervised learning on this, I saw these bands. If I look, these condition alerts here, those are the event frames that came from Pi that really recognized a problem with the drop in here. What I did is take the unsupervised learning that Falkonry did and put in some other labels for early warning. So there's clearly a condition of onset before the condition alert that Pi recognized, and then there's a normal condition before this. Again, this example is somewhat simple and contrived, but this pattern is always done by our customers, where basically you have some known condition like a shutdown or a strip and clean, and then what the customers do is, based on the unsupervised results, look for precursor conditions that they can label that will give them advance notice of that event that's going to happen. And in the case of the mine, that ended up being 12 hours in advance of the shutdown, and that there was an accumulation. Things even happened much earlier, were showing up in the currents and the temperatures early in that stage for them. And so then once that's done, you can see how when I train the system, now given these labels, it's able to start seeing these transitions into this early warning state. And then there's even further breakdown of differentiation between these different states as it's going across. So then you're able to recognize that pattern in the future based on a few examples from an early history period. So Falkonry is typically used with an agent like this Pi agent to create the data streams. It all based mode of interaction, which is useful when you're just exploring historic data, looking for patterns, using that to test the models against that data in order to see, can I find useful patterns here? So I'm going to show how we would do that with real data that comes out of a university lab where someone basically instrumented human subjects with 5 sensor locations. So they put a sensor pack on their torso, on each limb, and then there was 3 axes of XYZ acceleration from each of those that's used as data. So the way you would create what we call a standalone data stream is you give it a name. So here I have some source data files. If we see what's in them, there's a timestamp. This is a Unix epoch time. There's an index for the person. So in this case, you can have multiple human subjects, just like you had the multiple machines, and then the 15 accelerometer readings. This is 20 hertz data collected from these subjects. So Falkonry has looked at the file, it extracted some of the structure, lets you do wide or narrow format. You can have different types of time formats. And then you need to tell the system if there's an index for the entity. And again, entity is a term we use that maps to element in Pi. The system examined this data, and it found the 15 signals based on looking at sample data. It believes they should be numerical, and it also believes it's sampled data. We support categorical data as well as occurrence style data. So if you had transactions like a purchase transaction or events where those events, the timing between those events matters and interpolation between them isn't appropriate, we can support that as well. So again, we're at the sort of starting point where we have an assessment, which is the result, but there's no models yet. It's still loading this data, so it'll take it a second before it shows up. It knows the structure of this data. Okay, so here we see we have 150,000 events for this period of basically 5 minutes. So again, we can see sort of a trace of some of the data. So here. So at this point, I would go and just create a model. I'm going to use the whole segment. I know sort of here 100 seconds is on the scale of 200 points. So I'm like 20 to 200 points. Again, some of this is just pragmatics to have it run. I know from this data set that's a good bounding on the windows. Okay, so then it's off running that model. So go back to the oven, find one that I already ran. So this is that same data set. It took 8.3 minutes to run the model. So the unsupervised results, it found 6 different conditions in this data. You'll see that sometimes it can't recognize the pattern. It's a outlier. This is really the anomaly case. So here there was two episodes where it basically assigned the unknown label. So in general, this can be used either outliers or in a case where there's a brand new pattern. So if you're running machine and some new state happens, the first time it sees it, when it's monitoring, it'll show up as an unknown, and that can be a flag to do further investigation, or that could be an anomaly that matters. So what I can do now is I can add fact data. So here I have from this university data. So what was happening is this university data allows you to take the actual recorded data from human subjects. It's split up into pieces so you can randomly assemble a theoretical or a potential path that someone could have gone through in different activities, so that you have a true way of testing whether your system's really recognizing what's going on. The verification data has a similar structure, has a start and end time, it has a person index, and then it has the name of the activity that they were doing. So here, I see that I confirm that the time structure, and it shows me that I loaded these 39 examples. So at this point, I can run a new model, and what's different here is I want to check the box for supervised learning. Okay, it's still loading. Let's make sure. So here it sees those same 39 examples I just uploaded. So now it's using supervised learning to apply those labels. So I have an example where I've done this already. So here we see that initial timeline. This is the set of examples that was loaded corresponding to that timeline, and then I can see the result of the model here. So what you'll see happen is it took those examples and generalized across the time frame and was able to fill in the vast majority of the time. So here it's actually 100% of the time it was able to match against one of the supplied conditions. So I subsequently then added additional data to really test this model against a new period of time. So here we'll see the case where I extended the time frame. I see some of the same conditions, but now I have these unknowns. The reason I have the unknowns, is that the second section of data actually included a fifth condition called jumping. So if I look here, I had some other sample examples here where, after this, I had labeled jumping that matched at least some portion of those conditions that were recognized as unknown. So this is really showing sort of the path sort of sped up where you build a model, new data is run against that. You find the conditions you found before, but you might find new ones, and then additional labels are applied, and then you learn again. So after this, we created a new model, ran that, and now we can see that in this period, most of those unknown areas have corresponded to jumping. And we can see that we're having a little trouble with the transition, so that over time, some additional labeling of some of those periods, if we're able to verify what the condition was, the model can be improved again. So then finally, we added yet more data, which purely for purposes of test. And we can see that we classified the new section, and there's still a few unknowns showing up and some unlabeled conditions, but we're getting reasonable resolution given that this is a pretty small set of data with not a particularly large amount of examples. So in a real situation, it really just takes continued effort to update the system with any known conditions. Where the system was right, you tell it was right. Where it was wrong, you tell it was wrong, and that the model will improve vitality over time. So here I can compare against the actual results that I know, because this again came from this data set where I have actual measurements of what the real condition was. And so here I wouldn't be super happy. I can see that I have a few problems with particular periods of time. But overall, it's doing a decent job of recognizing this given the data I supplied it.
Appreciate your attention, and we hope to speak with you soon. Thanks very much. Have a great day, everyone.